A new scientific analysis of rare meteorites is bringing the prospect of asteroid mining closer to reality, moving it from the realm of science fiction toward a tangible, though complex component of humanity's future in space. The research, led by the Institute of Space Sciences, ICE-CSIC, and published in the monthly notices of the Royal Astronomical Society, provides a critical bridge between laboratory studies of meteorites on Earth and the practical challenges of identifying and extracting resources from their parent bodies in the solar system. The core mission of the study is to understand the precise chemical makeup of asteroids, assess the viability of extracting materials from them, and guide future missions in selecting the most promising targets for both scientific inquiry and in situ resource utilization, ISRU. The study focuses on carbonaceous chondrites, a rare class of meteorites that account for only about 5% of all meteorite falls on Earth. Their rarity is due to their fragile nature, which causes many to disintegrate upon atmospheric entry. Those that are recovered are often found in pristine environments like the Sahara Desert or Antarctica, where preservation conditions are optimal. Scientifically, these meteorites are invaluable because they are believed to originate from C-type asteroids, carbon-rich, ancient, and largely undifferentiated bodies. This means they have not undergone significant internal melting and separation of elements since the solar system's formation 4.56 billion years ago. Consequently, they act as time capsules, preserving primordial material and chemical clues about the early solar system. As explained by lead author Josep M. Trigo Rodriguez, an astrophysicist at ICE-CSIC, these meteorites sample small, undifferentiated asteroids and provide valuable information on the chemical composition and evolutionary history of their parent bodies. For over a decade, the ICE-CSIC research group has specialized in studying the physical and chemical properties of asteroids and comets, designing experiments to understand how processes like collisions and solar heating affect their surfaces. The Institute also serves as the international repository for NASA's Antarctic meteorite collection, giving the team direct access to these rare samples. The published work represents the culmination of years of team effort in selecting, requesting, and analyzing specific carbonaceous chondrites. To translate meteorite data into insights about asteroids, the research team undertook a meticulous process. They first selected and characterized 6 of the most common types of carbonaceous chondrite meteorites. These samples were then subjected to detailed chemical analysis using mass spectrometry at the University of Castilla-La Mancha, performed by Professor Jacinto Alonso Azcárate. This technique allowed the scientists to determine the precise elemental and isotopic composition of the meteorites with high accuracy. The goal of this precise measurement was twofold. First, to strengthen the classification linking specific meteorite types to families of C-type asteroids, and second, to create a benchmark for assessing the potential economic viability of extracting resources from these asteroids. By understanding the exact mineralogy and abundance of elements in the meteorites, researchers can infer what their parent asteroids contain and evaluate whether the concentrations of valuable materials would justify the enormous technological and financial investment required for extraction. The study yields several crucial conclusions that temper expectations while providing a clear path forward. Like the challenge of abundance, a central finding is a dose of realism regarding the immediate economic prospects. As noted by pre-doctoral researcher Pau Grebol Tomas, while the diversity of minerals in these meteorites is scientifically fascinating, most asteroids have relatively small abundances of precious elements. The primary objective of the study was therefore to determine to what extent their extraction would be viable. The analysis suggests that mining typical undifferentiated asteroids, the primordial remnants that are the direct parents of chondritic meteorites, is currently impractical from a purely economic standpoint focused on precious metals. The primacy of water, For near to midterm space exploration, the research identifies water as the most viable and critical resource. Water can be split into hydrogen and oxygen to create rocket fuel or used directly for life support. The study emphasizes that asteroids which have been altered by water and are rich in hydrated minerals, water-bearing minerals, should be the priority targets. Trigo Rodriguez states that, for certain water-rich carbonaceous asteroids, extracting water for reuse seems more viable, either as fuel or as a primary resource for exploring other worlds. Identifying promising targets, the team identifies a more promising class of asteroids for future mining efforts. Relatively pristine bodies that display specific mineralogical signatures, particularly of olivine and spinel. These asteroids may offer a more favorable balance of materials. However, confidently identifying such candidates from Earth-based telescopes remains challenging. The heterogeneity of asteroids. The research underscores that asteroids are not uniform resource deposits. Their composition is heavily influenced by a long and violent evolutionary history involving collisions and close passes to the Sun. As Trigo Rodriguez explains, if we are looking for water, there are certain asteroids, which, conversely, will have fewer metals in their native state. This inherent variability means that careful asteroid-by-asteroid classification and prospecting is essential. A one-size-fits-all approach to mining will not work. The study clearly distinguishes between the scientific return of sample return missions and the engineering challenge of industrial-scale extraction. Co-author Jordi Ibanez Insa, GEO3BCN CSIC, highlights a key issue. While many small asteroids are covered in a layer of loose fragmented material called regolith, which would facilitate collecting small samples, developing large-scale collection systems to achieve clear benefits is a very different matter. The core technological challenges are profound, like low-gravity operations. Extracting and processing materials in microgravity requires entirely novel robotic systems and techniques. Material handling, anchoring, and preventing debris from floating away present significant hurdles. Processing and waste management. The on-site processing of asteroid regolith to extract water or metals, and the management of the resulting waste, are complex problems that must be solved and their environmental impact in space mitigated. Economic and engineering scale. Moving from kilogram-scale sample return to ton or thousand-ton scale resource extraction represents a quantum leap in engineering. Trigo Rodriguez stresses the need for companies capable of making decisive steps in the technological development necessary to extract and collect these materials under low-gravity conditions. Despite these challenges, the researchers frame them as surmountable with time and investment. Pau Grebel Tomas draws a parallel to past ambitions. It sounds like science fiction, but it also seemed like science fiction when the first sample return missions were being planned 30 years ago. The findings of this research have broad strategic implications that extend beyond mere mining, like enabling long-duration exploration. The team anticipates near-future progress driven by the needs of lunar and Martian exploration. Using resources found in space, like asteroid-derived water for fuel, could drastically reduce the cost and increase the sustainability of long-duration missions by minimizing the need to launch everything from Earth's deep gravity well. Synergy with planetary defense. The research highlights a powerful synergy between asteroid mining and planetary defense. The detailed characterization needed for mining is identical to that required to understand the composition and structure of potentially hazardous asteroids. Trigo Rodriguez envisions a long-term possibility where we could even mine and shrink potentially hazardous asteroids so that they cease to be dangerous. Furthermore, concepts like capturing small, water-rich near-Earth asteroids and placing them in a stable orbit, e.g., around the Moon, for study and use serve a dual purpose. They provide an accessible resource depot and allow scientists to study a potential threat up close. The path forward: sample returns and prospecting. The researchers emphasize that the next essential step is to pair detailed laboratory studies of carbonaceous chondrites with new sample return missions. Missions like NASA's OSIRIS-REx and JAXA's Hayabusa 2 have begun this work. Future missions targeted at specific asteroid types are needed to ground truth the meteorite-asteroid connections made on Earth. Only by retrieving pristine samples from carefully selected asteroids can scientists definitively confirm their composition and test extraction processes in simulated environments. In summary, this analysis from ICE-CSIC and collaborators provides a sober, science-driven assessment of asteroid mining. It shifts the narrative from a simplistic gold rush in space to a more nuanced, stepwise strategy. The immediate economic extraction of precious metals from common, undifferentiated asteroids is deemed impractical. Instead, the viable path forward prioritizes water as the key resource, targets specific asteroid types with olivine spinel signatures, and relies on continued sample return missions and parallel technological development in low-gravity robotics and processing. The ultimate value of this research is its integrative vision. It positions asteroid resource utilization not as an isolated goal, but as an endeavor deeply connected to planetary science, the sustainable expansion of human presence in the solar system, and the enhancement of planetary defense capabilities. By rigorously decoding the messages held in rare meteorites, scientists are not only illuminating the origins of our solar system, but also drafting a practical, albeit challenging, blueprint for humanity's future as an interplanetary species. The dream of using space resources is moving closer to reality, but its realization will be guided by meticulous science, strategic prioritization, and breakthroughs in engineering,